Hi, my name is Max, and today we've got a really cool topic to talk about. It is going to get a little confusing maybe, but I personally love this topic and it's been getting a lot of attention recently, so after somebody asked me to make a video on it, I thought there'd be no better time. So, of course, if you read the title of the video, you'll know I'll be talking about quantum entanglement. Now, before we jump right into what quantum entanglement is, I want to just throw a little bit of background out there. I want to start by defining a wave as used in science. So a wave just means energy that propagates from one place to another. If it travels and propagates, it's a wave. So waves are also another way to describe particles. That's what's called wave-particle duality, where it acts as a particle, like saying a tennis ball would be an oversimplification, but just a physical object in a defined place with very defined everything, and a wave which is propagating, moving, changing position. So keeping this in mind, let's say we have a wave or a particle that's just kind of chilling in space. Now, one thing we know about this is it's got a few inherent properties. One of those properties, for example, could be what's called spin. And spin can be up spin, down spin, left spin, right spin. Putting a word in front of it is only useful kind of for us thinking about it, because in space and quantum mechanics there is no such thing as direction, at least the way we think of it. But the point is, you don't know if it's up or if it's down. And until you do know, it's both. That is the concept of superposition. Now, the way we would describe this mathematically is what's called a wave function. And I'm not going to get into the math of that too deeply, but all you need to know is we can't observe a wave function on its own, but we can observe its absolute value squared. What that means is that as we observe a particle, we're doing what's called closing that, collapsing that wave function. And that's because there's a window of possibility within that shrinks as you observe it to a single point. So let's say we've got our particle right here, and we don't know if it's up or down. Well, we get our observation equipment, whatever it may be, for whatever we're observing, and we look at it. Well, as we look at it, it'll no longer be up and down. It'll either be up or it'll be down. Let's say this one's up. Well, something really cool can happen as well. And that's actually going to be where we start our video. So let's say this one's back in a superposition we don't know, and all of a sudden it's got another particle right there. And that particle also is in a superposition of spinning up or down. Now, when this happens, something called an entanglement can happen between these two particles. And that's basically when you say, well, this one is up and down, and this one is up and down, so they're going to kind of cancel out. If you study physics, you'll know kind of a huge concept in the universe is netting out to zero. And that's exactly what these two particles want to do. They want to net out to zero. So let's say I observe one particle. Let's say we have particle A and particle B, and I observe particle A. And let's just say it has up spin. So I can take out the down arrow. What's the spin on particle B? Well, like we said, it likes to net zero, so we can know immediately, don't even need to look at it, that it's down spin. So why is this weird? That seems kind of straightforward. Well, it's kind of the basis of the EPR paradox, which is a paper by Einstein and a few other contemporaries. And without getting too deep into it, what would happen, you think, if particle A and B are no longer right next to each other? What if they're on opposite sides of the observable universe? I've got particle A over here in its superposition, particle B over here in its superposition, and between them all we've got the entire observable universe. Apologies for my bad handwriting. That's obviously a long distance, and mechanics, everything we've known, says that if I want to send information from A to B, it's going to take a long time. It's going to take several years because, well, the observable universe is huge. It's several light years large. So there would be no way for me to instantly send the message from A to B, right? Well, what's kind of cool and what you have to remember is this isn't necessarily information as we define it being transferred. I observe A, and it's up instantaneously so faster than the speed of light, faster than anything. Instantaneously, the wave function collapses for B. And that's because we know that B has to be opposite to A, because otherwise it wouldn't net zero. And so yeah, that's really cool because that means there is something faster than the speed of light, even if it's not information or technically travel. So mechanics isn't technically broken by that, but it's a really cool addition to that. What's really cool though about entanglement is it doesn't have to be with just one property. I mean, okay, up and down spin. It can also be with left and right spin. It could also be with momentum or position or literally any property of a particle. And that's just what's so kind of mind-boggling but cool about it, is literally anything about this particle could be entangled with that particle. And so long as I know something about this one, or I know something about this one, I know everything about the opposite. Now, one quick note before I go. I've been using up spin, down spin, left spin, right spin, just casually. It is not like classical spin. If you were to zoom in to a particle like an electron, you wouldn't see it just kind of rotating in a circle the same way this would if I spun that like that, for example. That's because waves and quantum objects don't behave the same way as macroscopic objects. If you're interested in electron spin or just particle spin in general, PBS Spacetime has a really good video on it that goes into a lot more detail than I really would like to. So I'd totally recommend checking them out. Otherwise though, I hope you enjoyed. Have a great day.